Okay, so we're going to put it all together. In other words, if we see a substrate and it has a leaving group on it, we want to know when we see something over the arrow that could be either a base or a nucleophile, whether it's going to do a substitution, which would mean we get the new group replacing it, or an elimination, which means we get the pi bond, or both. Which one? So this is all about E1, E2, SN1, SN2, making a judgment call when possible. So when you're asked to make that kind of judgment call, which one's going to happen? In other words, we won't be given the product, we'll be given the substrate and stuff over the arrow, and we have to make a judgment call. I'm going to ask you to kind of go in this order. So we'll kind of set up a flow chart, and then we'll have a shorter checklist to condense it a bit, because a flow chart's not something we could write every single time we do a problem. But it helps to kind of cover our understanding in the beginning. We're going to look over the arrow, and we're going to say, is what's over the arrow a better base or a nucleophile, or do we even know that answer yet? Well, in terms of its base or nucleophile and its strength, we're going to ask that question. If it's weak, we're talking water, alcohol, etc. Okay. Then we're in the SN1, E1 category. You can use heat to favor elimination, but that's about all. Otherwise, it's going to be pretty equal. Other things to consider: must be primary, secondary, or tertiary, because remember we have a carbocation. So no primary or methyl. Could be primary with resonance, of course. Okay, so how about the other scenario? What if we have a strong base / nucleophile? So if our answer to the question is that, hey, what's over the arrow? Something that's a weak base or nucleophile, we do SN1 or E1. We're in the first order land. If we say it's a strong base or nucleophile, we might ask this question next. Is it bulky? Why do we ask that? Well, you might have noticed the trend. The things that like to be bases only are too bulky to be good nucleophiles. So we're talking DBU, LDA, things that are T-butoxide and bigger, right? So let's say bigger, greater than or equal to T-butoxide in terms of alkoxides. DBN. So these are bases. These act as bases only because they are just too bulky to be a good nucleophile. Now let's think about the scenarios that are not bulky. So if the answer to that question is no, we're thinking the other alkoxides, like ethoxide, methoxide, right? Those are great bases and great nucleophiles. So we cannot judge whether it's substitution or elimination yet. We have to start looking at the next thing. We have to look at the nature of the substrate. In other words, is the substrate primary? Sorry, my pen is going slow. Here we go. Primary, secondary, or tertiary? Okay, so if it's primary, we are not sterically hindered to backside attack at all. We are at the periphery of the molecule, so SN2 is very easy to accomplish. So SN2 is actually favored for smaller primary alkyl halides or methyl halides. So primary or smaller. Secondaries, where we got to ask ourselves again, well, it could actually go both ways. So let's ask ourselves, do we have something that's a better nucleophile or a better base? Look at what's over the arrow. Things that are nucleophiles only. Are going to go SN2. What's a nucleophile only? Things that when they grab an H, they become a strong acid. So something like nitrile, cyanide anion. So I'll just say EG. What about something, or the halides, right? What about something that would be a reasonable base? So alkoxide, amides, they'll go E2. So in other words, two ways to arrive at E2 so far. Something that's can only be a base right away. We'll just automatically go the E2 path. But we will consider the substrate path if it's not necessarily a bulky base, but better at being a base, right? If it's secondary. Tertiary, so in other words, we prefer second order for secondary. Tertiary will not be able to do which one of the second orders? SN2. Impossible. So E2 is where it's at. But we have to have an anti-beta H, right? If not, we go back to here. Because it can't do SN2. So it will react. It just goes to one of the slower reactions, i.e. the first order reactions. So another way to do this logic diagram is to put it in a table. Klein has a really nice one. And I took this from the Klein textbook, where it's focused mostly on, so doesn't have as many specifics, but we want to get away from too many specifics because we don't have time to write a flow chart out every time. So this was kind of a big summary picture. And now we're going to try to distill it into smaller pieces that we can use, smaller chunks. So in this table, which is kind of quite nice way to look at it, we have the substrate here, primary, secondary, tertiary. We have what's over the arrow here, something that's more or less a base but never a nucleophile, something that's more often a base or equally a nucleophile, something that's rarely a base, mostly a nucleophile, or something that's pretty weak at both. Notice this category, weak at both. Only thing that ever reacts is tertiary for the most part. SN1, we'll see this doesn't agree with everything. We'll see examples where secondary reacts with other sources, namely any old problems I have from other resources. So this is kind of a borderline case, but we'll follow this in terms of his homework problems. But SN1E1, tertiary, we are not going to see any second order with tertiary, right? That's only when it's a weak base, weak nucleophile. That's this region. We will see tertiary elimination with anything that could be a strong base. That'll be favored. If it's only a nucleophile and not a good base, then we'll see back to this category because we can't do SN2. Secondary is where we could do E2 or SN2. And primary, we'll see more E2 dominate. SN2 dominate. So it depends on the situation, obviously, but we try to make a trend so that we can kind of carry this through. Let's put this into practice with some problems. Nothing will really, proof is in the pudding, as they say. All right. So what I actually am going to do is make this even simpler and go back to this little checklist right here. So what we could really do is summarize this and say, what does this all mean? SN2 is actually favored if we look at the substrate and we see that it's primary. It's always going to be SN2. If not, we'll try E2. Anything else that's a bigger leaving group, we're going to go back to SN2. Then finally, we'll consider these together. And don't forget about carbocations. Okay? So let's do that list. Okay, so I'm going to, okay, so let's do this problem. I'm going to make that list that we had above. And oftentimes we'll have to expand upon it a little bit, but it's a good starting point. So I'm going to say, get this little cheat sheet ready for me. SN2, if and only if primary Rx. Then I look at E2 for all other cases if possible. I go back to SN2 for other cases. And lastly, if I have to, I work my way down to the first order land. All right. Let's look at what we have here. I'm going to try to get an SN2 to work. I have a primary alkyl halide. No, I don't. I have a methyl halide. So MEX. That's actually even smaller. SN2 it is. I stop there. Okay. So simple enough. We remember good old SN2. Kick that off. Actually, I don't like that. It's not drawn out. So let's draw out all our bonds. Yeah, we have a polar protic solvent, but that's not enough to stop an SN2 from happening. So we have MECN. All right, simple enough. Let's see if this will help us with a more complicated case. A lot more going on there, right? Let's make our cheat sheet again. A little checklist. SN2, if and only if primary Rx. Then we try an E2. We have to know all the criteria for these things for this little cheat sheet to work. So it takes some studying to get here, but it's the shorter way than an entire page of a flowchart, right? Okay. SN2, if and only if primary alkyl halide. Let's look at what we got. Oh, here's our substrate. I would not describe that as a primary carbon that it's on. Definitely secondary. Rule that out. Next, I'm going to try to make an E2 happen. So these are supposed to be in order of thermodynamic preference, if it's possible. You just have to have the conditions to make it possible. So, can I do an E2? What does an E2 need? I need an anti-beta H. I need a base. Let's look over the arrow. T-butoxide is a base, check. Let's fill in our, since we found our leaving group, that means this is our alpha carbon. Let's find our beta carbons. Beta 1, beta 2. Oh, we definitely have beta carbons. That means we have beta H's. Here's a wedge. That's beta 1 H. And then this is a methyl, which actually has 3 H's. So yes, we will be able to make a beta H anti to that. Right? That means who wins? E2. We're going to have an E2 product. We go on to do the E2 thing. Draw your E2 product here. Be mindful of the E versus Z product. Zaitsev versus Hoffman alkene. Now, I've done several of these for you. It's your turn. You fill this in. But I got you there. I got you to the point where we knew we needed to do E2. But now you can have some practice with that and check your answer with me after. Let's do another one where we need to make a decision. What do you think? we have our cheat sheet we could start with. Remember, SN2, if and only if, primary Rx or smaller. E2, then SN2 again, then E1 slash SN1, first order. All right, let's look for our primary alkyl halide. Well, sorry, we're not going to get it. It's tertiary. Okay, so there's our alkyl halide. Let's look for a beta H. Can we do E2? We need a beta H. There's a alpha carbon. There's beta, beta with H's. We do have beta H's. Okay, so that means we need a strong base if we're going to do E2. Nope, nope, not a strong base. Go back to SN2. Oh, SN2 is not allowed. It's tertiary. It's also not a strong enough nucleophile. Our only choices. We're down to the bottom feeders here. We don't love to do the first order, but that's our only option. So we need to draw the E1 and the SN1 product, being mindful of possible rearrangements. Same first step for both. Leaving group leaves. We have a nice tertiary carbocation that's resonance stabilized. So that's about as good as it gets. So we can just keep going. We don't have to worry about resonance. But we have both fates to consider. We have the E1 path and the SN1 path. So SN1 would mean that the incoming water acts as a nucleophile. And now look at that. That water is attached at the oxygen. It brought everything with it, but clearly we're not going to leave it like that. We need to neutralize. Who's going to do that job? We can take more water to do that. Never leave it like that. Always end with a neutral product. All right, that's what our SN1 product looks like. We have an alcohol where we used to have the alkyl halide. We replace the I with the OH. Let's do the elimination path. If we do E1, that means that water is our base. That means we need to find a beta H. Let's take this one. Could have taken the other one, they're the equivalent, right? So take the lone pairs from water, grab an H, fill that open octet with electrons to form the pi bond. Oh, how lovely. We are done. Much shorter mechanism, right? Here's our E1 product. We form both. Okay, so that's an example of how we get to the bottom of that list. Let's do a couple more. Halide? No, in fact, that's a bad leaving group. The only time we use OH as a leaving group is when we could turn it into a good leaving group, like water or acid. And that's not an option here. So you will see that ever so frustrating option, N.R. That means no reaction. We do not have the conditions required to satisfy anything on our checklist. Let's move on. I want you to give this a try. Use the checklist, SN2, go back to, if that fails you, go to E2. So remember, that's if and only if it's a primary Rx or smaller. If that's not the case, you move to E2. If E2 works, you're done. Otherwise, you go down to SN2. If that fails you, then you could consider SN1/E1. Okay, leaving that for you. Check your answer when you're done. Good luck.